So the concept of parallel processing can be used to lower the power of the DSP system. Okay, so earlier we have seen that the concept of pipelining can be used to lower the power. Now in the similar way, parallel processing can also be used to lower the power of the overall DSP system. So again, comparing the two systems based on the following parameters. So if clock period of the system is Tc, so the same L level parallel process system can also be driven by a same clock, because we have just duplicated the system L times, and each of the system can be driven by same clock speed. If the sampling rate of the system sequential system is key, so um, sampling rate of this parallel process system will be L times k, provided that the clock rate of both the systems are same. In that case, it will be L times k. If the total capacitance of the system is C total, so the total capacitance for this systems will be increased by L times, that is L into C total, and the capacitance of critical path is C charge, so the capacitance of critical path will be same as C charge, because the L systems are in parallel, they are not in series, so the C charge remains same. So if the sampling time for this system is Ts, so the sampling time for this system can be written as Ts by L. Okay, and these all comparison are based on the fact that both are driven by same clock. So the sampling time of this system is Ts, and the sampling time Ts dash for this system can be written as a Ts by L. Okay, so as the sampling rate is increased by L, so sampling time is decreased by L. So in this case, sequential system clock period is equal to sampling period, and in this case the clock period is L times the sampling period Ts dash. Talking about the power dissipation of the system, so power dissipation can be given by this formula: C total capacitance of the system multiplied by supply voltage square into frequency, that is 1 by Tc. And power dissipation of the system can be given by L into C total, because the total capacitance is increased by L times, into V naught square into 1 by Tc, because both the systems are driven by same clock speed. Okay, that is 1 by Tc. So the propagation delay, that in turn is equal to the minimum clock time, can be given by C charge into V naught divided by k minus V naught minus Vt square, and in this case the propagation delay, that is equal to Tc minimum, that is also given by the same formula. Okay, so this Tc can be always greater than TPD, there is no problem. Tc minimum should be equal to TPD, there is no problem in keeping Tc greater than TPD. Now till now the clock period of both the system is same, and as a result, the sampling rate of the system is L times greater than the sampling rate of the system. So now what if the sampling rate of sequential system and parallel system are kept same? Means the sampling rate of the sequential system is also key, and parallel system is also key. So this means that this system is being operated at the same speed at which the sequential system is being operated. Okay, so this can be done by decreasing the clock rate, or you can say increasing the clock period of the parallel system, and you have to increase it by L times, and by doing this the C charge of the critical path can now charge and discharge in a larger amount of time, and since it is now having more time to charge and discharge, the supply voltage V naught can be reduced. So it can be reduced to, let's say, beta V naught, where beta is less than 1 greater than 0. Okay, so this can be proved mathematically also. So the formula for the propagation delay, or you can say clock period, is given by C charge into V naught divided by K minus V naught minus Vt square. So if you increase the clock period by L times, so if LHS is increased by L times, RHS should also increase by L times, and this C charge and K are fixed, and in this Vt is fixed. Okay, so this term cannot be changed. This factor should be increased by L times, and this can only be achieved when you reduce V naught accordingly. Okay, so if T clock is increased by L times and supply voltage is beta V naught for L level parallel system, so the formula is modified to L times Tc, that is equal to C charge multiplied by beta V naught divided by K into beta V naught minus Vt whole square, and Tc is given by C charge into V naught K into V naught minus Vt square. So Tc is given by C charge into V naught into K times V naught minus Vt square. Same for both the cases. Okay, so now substituting the Tc value of Tc into this equation, the equation will be modified to C charge into V naught divided by K times V naught minus Vt whole square, and this side we have C charge beta V naught divided by K times beta V naught minus whole square. So common terms get cancelled, and we have L times beta V naught minus Vt whole square, and on the right hand side we have V naught minus Vt whole square. So beta can be obtained by solving this quadratic equation. Okay, after obtaining beta we can calculate the power dissipation of this parallel circuit. So it is given by L into C total into beta square V naught square into 1 by LTC. Now the clock period is increased by L times, and proportionally frequency will be decreased by L times. So this L get cancelled with this L, and we have C total into V naught square into 1 by Tc multiplied by beta square. So this term is power dissipation of sequential circuit multiplied by beta square. Okay, and since beta is less than 1, so power reduction factor is beta square. Okay, p sequential multiplied by a value less than 1. Okay, so this will be reduced as compared to p sequential, and the factor is beta square. So this is how you can reduce the power of the DSP system by applying the concept of parallel processing. Keep the sampling rate same as that of the single input single output system, and in that way you can increase the clock period and you can decrease the supply voltage, resulting in a less power dissipation.